Hello everyone, welcome to Applied Chemistry Tutorials. Today we will talk about calculation of molecular weight of polymers. We'll start with molecular weight distribution. Polymers are collection of long chains of different molecular weights. Instead of specific molecular weight like small molecules, polymers usually have a molecular weight distribution around a mean value which is represented by average molecular weight. The molecular weight distribution of polymer is represented by Gaussian distribution. Average molecular weights of polymer are expressed as number average molecular weight or Mn bar, weight average molecular weight or Mw bar, Z average molecular weight or Mz bar, and viscosity average molecular weight or Mv bar. We have discussed the concept and expression of all these four molecular weights in our previous video. I will provide the link here, you can go and check it. In this video, we will talk about the different measurement techniques of the polymer molecular weights, and we will also show some example problems to find out the polymer molecular weights. Let's start with the measurement techniques. Number average molecular weight or Mn bar can be determined by end group analysis or by measuring colligative properties like ebullientiometry, cryoscopy, and osmotic pressure or osmometry, etc. Among all this technique, osmometry gives the value which is practically possible to measure. Weight average molecular weight or MW bar is measured by light scattering method, neutron scattering method, etc. Z average molecular weight or Mz bar is determined by ultracentrifugation technique. Viscosity average molecular weight or Mv bar is calculated from Mark-Houwink equation, which is expressed as eta equal K multiplied by Mv bar to the power alpha, where eta is intrinsic viscosity and it can be determined by measuring the viscosity of polymer solutions at different concentrations and then extrapolating to find out viscosity at zero concentration. That means from the intercept of the plot. K and alpha are Mark-Houwink parameters and depend on particular polymer solvent system. All above mentioned methods are absolute methods and insufficient to provide entire molecular weight distribution of a polymer sample. So the most frequently used method in industry as well as in academia is gel permeation chromatography or GPC. It is a technique which provides molecular weight distribution information in the entire range. But GPC is a relative method. It requires standard samples of known molecular weight for calibration. Molecular weight of the standard samples, which are essentially monodispersed samples, must be determined by some absolute methods. So, GPC in turn also utilizes the data from the absolute methods as we described in the previous slide. GPC is based on the principle of size exclusion chromatography or SEC. Depending on the size of the molecules, which in turn depends on the molecular weight, different fractions of polymer samples are obtained in GPC. The concept of GPC and how to calibrate the GPC data and also how to calculate the polymer molecular weight utilizing the GPC data, all these things we will discuss in our next video. Next, start with the example problem. The problem number 1. Consider a polymer sample with following fractions. Calculate number average molecular weight and weight average molecular weight of the sample. So the number of moles represented by Ni and molecular weight represented by Mi for each fractions are provided in this table. Suppose for the first one the number of moles are 0.05 and its corresponding molecular weight is 5000. For the second fraction the number of mole is 0.12 and its molecular weight is 10,000 gram per mole and so on. If we need to find out number average and weight average molecular weight, let's see the expression of these two. Number average molecular weight or Mn bar is represented by summation of Ni Mi from I equal 1 to infinity divided by summation of Ni from I equal 1 to infinity. And Mw bar or weight average molecular weight equals to summation of Ni square from I equal 1 to infinity divided by summation of Ni from I equal 1 to infinity. So obviously we have to find out Ni multiplied by Mi and Ni multiplied by Mi square. So we can calculate Ni by multiplying Ni with Mi. So 0.05 multiplied by 5000 and we'll get 250. For the next fraction 0.12 multiplied by 10,000 we can get 1200 and so on. For the NiMi square we can multiply NiMi with Mi. 250 multiplied by 5000 we can get 1,250,000. Similarly we can calculate for the rest of the fractions. Now we need to find out the sum of the NiMi by adding up all these values. This is the sum. And sum of the NiMi square values by adding up all these values. This is the summation of NiMi square. And we also need the summation of Ni. So we can add up all these values and get the summation of Ni. Now if we plug in the values in the Mn bar expression, then we can get Mn bar as 25,427 gram per mole. Similarly, we can get MW bar as 26,205 gram per mole. Sometimes you can see instead of number of moles, weight of the polymer fractions are given. So you can utilize easily Wi in place of NiMi to find out Mn bar or MW bar. Similarly, you can find out NiMi square by multiplying Wi with the respective molecular weight. So this Mn bar expression will be now turned as summation of Wi from I equal 1 to infinity divided by summation of Wi over Mi from I equal 1 to infinity. And the Mw bar expression will be summation of Wi multiplied by Mi from I equal 1 to infinity divided by summation of Wi from I equal 1 to infinity. You can see you can get the Wi value, Mi value and Wi Mi value everything from this table. Just you have to rewrite the expression. Now let's see the polydispersity index. It shows the breadth of the molecular weight distribution and it is the ratio of weight average molecular weight to numbered average molecular weight. So if we plug in the values from MW bar and Mn bar from the previous slide to this expression, we can get PDI equal 1.03. So we can clearly see that weight average molecular weight is greater than number average molecular weight, as we have also shown it in the Gaussian distribution of the polymer molecular weight, and also it has the PDI value only as 1.03, which represents very narrow distribution. Please note that MW bar or weight average molecular weight is useful to characterize polymer properties related to its size, such as viscosity, whereas number average molecular weight or Mn bar is useful for analyzing the polymer properties which depend on number of polymer molecules, such as reactivity of a polymer sample. Now let's discuss little bit on degree of polymerization. In the previous problem, instead of molecular weight, if degree of polymerization and molecular weight of repeating unit were provided, then how will be the calculation? Suppose only number of moles and degree of polymerization is provided, and it is said that molecular weight of repeating unit is 100 gram per mole. Then to find out the molecular weight of polymer, that means molecular weight of each fractions, you can utilize this formula. This is the formula of degree of polymerization, which equals to molecular weight of polymer or Mi divided by molecular weight of repeating unit or M naught. Therefore, Mi equal dP multiplied by M naught. Here M naught is 100 gram per mole and dP for each fractions is given in the table. So you can calculate the molecular weight of each fraction by multiplying dP with 100. So 50 multiplied by 100 is 5000, 100 multiplied by 100 is 10,000 and so on. So we got the molecular weight of each fractions. Now rest of the calculation just like before. You find out NiMi by multiplying the Ni with Mi. Then you find out NiMi square by multiplying NiMi with Mi. You obtain their summations and then you plug in the formula of Mn bar and Mw bar just like before. So I am not showing it here again, but you can go back in the previous slides and check. Okay, moving forward to the problem number 2. In this problem, we'll highlight the significance of MW bar. Consider 7 blocks of different weights as given below. Calculate the average weight. Here we have 7 blocks and each has 7 different weights. Here weights of the each block represents the molecular weight of the polymer fractions. Just assume it. We can calculate the Mn bar and Mw bar by utilizing the formula. So let's calculate Ni Mi by multiplying Ni with Mi. So 1 multiplied by 100, 100, 1 multiplied by 110, 110 and so on. And Ni Mi square by multiplying Ni Mi with Mi. So 100 multiplied by 100, that means 10,000 and so on. We find out the sum of this Ni Mi square and the Ni just like this, and we plugged in the corresponding values to get the Mn bar as 1619 gram and Mw bar as 4890 gram. Please note that here I mentioned the average weight as gram because this is just block to make the example simple. The Mi actually represents in real case the polymer fractions. Now we can easily see that Mw bar is very high, 4890 gram compared to the Mn bar which is 1619 gram. So Mw bar is clearly favoring blocks of higher weights and a better representation to find average molecular weight of polymer samples containing high molecular weight fractions. Therefore, although we calculate the Mn bar, but for the polymers which contain few fractions which has very high molecular weight, we always use Mw bar. So this slide gives you the idea of why we compute Mw bar although we have the data of Mn bar. Let's move forward to problem number 3. This is the problem related to viscosity average molecular weight. Let's consider 5 different monodisperse polystyrene standards with molecular weights and intrinsic viscosities of their solutions as given in the table below. Find out Mark-Houwink parameters K and alpha values. So here are the molecular weight and intrinsic viscosity of 5 different standards. The standards are monodisperse polystyrene samples. So this is the Mark-Houwink equation, eta equal K multiplied by m to the power alpha. Here m means viscosity average molecular weight or MV bar. We have to find out the K and alpha values. Those are Mark-Houwink parameters. So if we take log on both sides, we'll get log eta equal log K plus alpha multiplied by log m. Now if we calculate log m, we have to take the logarithm of molecular weight. So log of 50,000 is 4.699, log of 80,000 is 4.903 and so on. And then to find out log eta, we have to take the logarithm of intrinsic viscosity. So log of 0.245 is minus 0.611, log of 0.423 is minus 0.374 and so on. Now if we plot this log m and log eta, where log m as x-axis and log eta as y-axis, then after fitting the data we can get this trend line equation y equal 0.834x minus 4.499. Now if you compare it with the straight line equation y equal mx plus c, then you can get the intercept and slope value. So let's rewrite this equation as y equal minus 4.499 plus 0.834x. So if we compare this equation with this expression, then clearly log k equal minus 4.499. Therefore k equal 10 to the power minus 4.499 and k equal 3.169 multiplied by 10 to the power minus 5 deciliter per gram. Similarly, we can get alpha equal 0.834. This is a unitless quantity. So we got the K and alpha values from this table. Next, moving forward with the second part of this problem. Now consider a polydispersed polystyrene sample with intrinsic viscosity as 1.1 deciliter per gram, measured at same condition as for standards. Suppose both the standards and samples were measured by dissolving it in benzene at 25 degrees centigrade. Now find out the molecular weight of the polystyrene sample. We obtained K and alpha value in the previous slide. Now provided here, the intrinsic viscosity of the polydispersed polystyrene sample is 1.1 deciliter per gram. The Mark-Houwink equation is eta equal K multiplied by m to the power alpha. So if you take log on both sides, so log eta equal log K plus alpha multiplied by log m. Therefore, if we plug in the value, then it turned to log 1.1 equal log 3.169 into 10 to the power minus 5 plus 0.834 multiplied by log m. By simplifying, we get 0.041 from log 1.1. Then from this expression, we get minus 4.499 plus 0.834 into log m. So, if we calculate the m value, we will get it as m equal 277,744. So our viscosity average molecular weight or MV bar equal 277,744 gram per mole. So this problem shows how to find out the viscosity average molecular weight utilizing the Mark-Houwink equation. That's all for today. In the next class, as we just described, we'll talk about GPC. Until then, please stay tuned with us, and if you like this video, please give it a thumbs up, share and subscribe to our channel. Thank you.